If we want to go out there and, and make sci-fi real, and be on other planets and go back to the moon, then we need big rockets.
In 1969, Apollo 11 carried humanity to the moon with one rocket, one mission, and one clear goal: to beat the Soviet Union in the space race. For a brief moment, the impossible was achieved, and the world believed that arriving the moon would soon become a simple routine. But more than 50 years later, no human has set foot there again, even as SpaceX regularly launch rockets and promises voyages to Mars. Why does reaching the moon remain so painfully difficult? The risks are higher than most people imagine. Catastrophic failures, staggering costs, and political hesitation still haunt every step, slowing progress at every turn. Yet our goals are now far greater than ever, building a permanent human presence, unlocking resources, and creating the foundation for even further journeys beyond the stars. Because if we did it before, why can't we do it again? Only better. And if even SpaceX and NASA struggle, what hidden barriers are still holding us back? In July 1969, Apollo 11 left Cape Kennedy on top of the mighty Saturn V rocket, the tallest machine ever built by humans at that time. It carried 3 astronauts, Neil Armstrong, Buzz Aldrin, and Michael Collins, into history. With one single launch, America reached the moon in just 4 days, fulfilling President Kennedy's promise. The mission was simple in design, but enormous in impact. Its goal was political victory over the Soviet Union, and it worked. The Apollo process looked straightforward compared with modern standards. The spacecraft launched, separated into modules, landed on the surface, and returned. There were no orbital refueling depots or international partnerships. Astronauts stayed less than 3 days on the moon before heading back home. Dr. Roger Launius, former NASA chief historian, explains that actually, Apollo was never built for permanence, but only for demonstration. Apollo 11 itself showed both the brilliance and the limits of that era. Armstrong and Aldrin walked on the lunar surface for just 21 hours, collecting rocks and planting a flag. Collins circled above in the command module, waiting for their return. President Nixon called them live from the White House, calling it the greatest week in the history of the world since creation. But once they came home, the technology was left behind. The simplicity of Apollo was possible because of the context of its time. The Cold War fueled urgency, and billions of dollars were poured into the program without hesitation. NASA could take risks that today would be seen as unacceptable. Former flight director Gene Kranz once said, "Failure was not an option, but the truth was that." Apollo succeeded by pushing through enormous dangers. That daring approach brought quick results, but left no lasting infrastructure. Artemis 3, planned for later this decade, is designed in a far more complex way. Instead of one vehicle, it uses many: NASA's Space Launch System, the Orion capsule, and SpaceX's Starship human landing system. Before astronauts even arrive, Starship must be launched into orbit and refueled multiple times by tanker versions of itself. Dr. Bhavya Lal from NASA points out that orbital refueling has never been done before, making this a giant experiment. This chain of steps shows why Artemis is slower and harder to execute. The role of SpaceX adds both hope and difficulty. Elon Musk promotes Starship as the vehicle that will make humans multiplanetary, but it is still unproven for crewed lunar landings. Several prototypes have exploded during test flights, and only a few have landed safely. Yet NASA believes Starship's scale and reusability will lower costs in the long run. Former astronaut Garrett Reisman, now a SpaceX advisor, says failure is part of the path to success, but with astronauts on board, the stakes are far higher. Unlike Apollo's quick visits, Artemis has long-term goals. astronauts will stay longer, build systems to survive, and prepare for a permanent base. This requires new life support, power, and transport technologies. Dr. Clive Neal, a lunar geologist at Notre Dame, stresses that Artemis is about building an infrastructure, not just planting a flag. The complexity we see today is a reflection of ambitions that go beyond the 1960s. Why would Artemis choose a path filled with more steps instead of repeating Apollo's direct route? And could this very complexity reveal that NASA and SpaceX are aiming for something greater than the moon itself? In the 1960s, NASA commanded nearly 5% of the entire U.S. federal budget, an amount so vast that it mobilized more than 400,000 engineers, scientists, and contractors. The Apollo program was fueled by Cold War urgency, with President Kennedy declaring the moon a battlefield of ideology. Dr. John Logsdon, founder of George Washington University's Space Policy Institute, explained that Apollo was a political act disguised as a technical program. Every dollar spent was tied to proving America's system superior to the Soviet Union. The moon landing became both a triumph of science and a weapon of soft power. Today, NASA survives on about 1% of the federal budget, and that small slice is spread thin across dozens of missions. Money is divided between the International Space Station telescopes like James Webb, planetary probes, climate satellites, and research grants. Artemis must compete for funding in a way Apollo never did. Former NASA Administrator Charlie Bolden has said, "Without a political enemy like the Soviet Union, the motivation to fund another Apollo-scale effort simply doesn't exist." Instead of urgency, Artemis advances slowly under the weight of compromise. The lack of Cold War rivalry has changed the very DNA of space exploration. Into this financial vacuum stepped SpaceX, carrying not only rockets but also private capital and ambition. In 2021, NASA awarded Elon Musk's company a $2.9 billion contract to develop the Human Landing System, the first time a private firm was trusted with putting humans on the moon. Musk called it the beginning of humanity's journey to Mars, framing Artemis as a stepping stone beyond. Dr. Lori Garver, former NASA Deputy Administrator, said, "The public-private model is not just about saving money, it's about unleashing innovation." SpaceX now finds itself as both a contractor and a symbol of the new space age. But the financial stakes are daunting even for Musk's empire. Development of Starship costs billions annually, with repeated test explosions burning through cash as well as hardware. Unlike NASA, SpaceX cannot rely on guaranteed federal appropriations. It must survive on contracts, investors, and satellite revenue. Each fiery failure is both a data point and a gamble with reputation. Professor Matthew Weinzierl of Harvard Business School notes, SpaceX's strength is its willingness to fail, but failure in a commercial environment carries risks Apollo never faced for SpaceX. Artemis is not just a mission, it is a survival test. What makes Artemis unique is the balance of public caution and private daring. NASA sets the safety rules and long-term vision, while SpaceX provides speed and disruptive engineering. Some critics argue this slows things down, but others see it as a way to combine the best of both worlds. Former astronaut Chris Hadfield describes it as an arranged marriage, awkward, but with the potential to achieve something neither could do alone. The Apollo era was about spending without limit. Artemis is about partnership without guarantees. If governments no longer act as blank check sponsors, can SpaceX truly carry the weight? And will this NASA-SpaceX partnership create a force strong enough to replace the raw urgency of a political space race? In 1967, a fire consumed the Apollo 1 capsule during a ground test at Cape Kennedy, killing Gus Grissom, Ed White, and Roger Chaffee inside the oxygen-rich spacecraft. The nation grieved, engineers redesigned wiring, materials, hatch mechanisms, and procedures, and the program accelerated toward the moon rather than retreating. Cold War pressure framed risk as necessary, and budgets, schedules, and politics pushed missions forward despite unknowns that today would halt a countdown. Space policy scholar Howard McCurdy observed that Apollo succeeded partly because society accepted higher risk as the price of prestige and technological dominance. That mindset shortened timelines and delivered a flag on the moon, but it never built margins or logistics intended for staying, mining, or permanent outposts. What worked in the 1960s could not last forever, and the same culture of risk would later collide with new expectations in a different era. The 21st century lives under a different compact with astronauts and taxpayers, and that difference shapes every decision inside Artemis. Challenger exploded in 1986, and Columbia disintegrated in 2003, tragedies broadcast live that scarred public trust and reshaped institutional memory. NASA responded with rigorous verification, independent review boards, hazard analyses, simulations, and documentation, tracing each requirement down to solder joints and software lines. Former shuttle commander Eileen Collins has said NASA must prove safety repeatedly, because a single loss can end a program and erase years of work. The result is slower progress, but also thicker defenses against preventable failure and expectations that safety survives leadership turnover, budget fights, media storms, shifting priorities, and election cycles. SpaceX approaches risk with a startup mindset that unnerves traditional observers, yet it remains central to how the company learns fast under constraints. Build, fly, break, capture data, and iterate. Starship prototypes have ended in fireballs, while Raptor engines, methane plumbing, guidance algorithms, and structures improved after each flight. Elon Musk argues that truly reusable rockets cannot emerge without many explosions during development, a logic difficult for regulators and legacy contractors to embrace fully. Planetary Society analyst Casey Dreyer agrees hardware can tolerate aggressive testing, but warns the philosophy must adjust when human lives and escape systems ride the vehicle. For SpaceX, visible failure is tuition and momentum. For NASA, visible failure is liability and hearings, and that difference colors every meeting and milestone. When the two cultures meet on Artemis, compromise is unavoidable yet potentially powerful if neither side erases the other's strengths or institutional knowledge. NASA requires multiple flawless flights, crew abort capability, hardened redundancy, exhaustive software validation, and strict configuration control across launch, docking, landing, and return. SpaceX pushes rapid iteration, short feedback loops, and designs for mass production, while learning to satisfy government oversight without losing momentum or engineering edge. Scholar Joan Johnson-Fries calls the partnership a marriage of convenience between caution and disruption, awkward at times but capable of extraordinary offspring when trust forms. The hybrid model can feel painfully slow, yet it may produce safer systems than Apollo and cheaper systems than legacy contractors working alone. Beneath engineering debates sits a question about values, because Apollo prized achievement over safety while Artemis seeks progress without preventable loss, and NASA carries public trust and congressional funding that demand caution. SpaceX carries urgency and ambition, pushing boundaries to lower costs and expand capability faster than government alone could manage or defend under political scrutiny. Former presidential advisor John Holdren warns that courage without caution is reckless, while caution without courage goes nowhere and leaves dreams stranded on paper. When harsh realities like lunar dust, massive engines, and strict timelines strike, can this fragile partnership truly endure? During the Apollo era, engineers built Saturn V, an 1,100-meter rocket that lifted over 3,000 tons and hurled humans beyond Earth for the first time. It remains one of the most powerful machines ever created, yet it was expendable. each launch discarding stages into the ocean. The detailed blueprints are incomplete, scattered, or lost in archives, and the veterans who knew the system best have retired or passed away. Rebuilding it now would require relearning from scratch, requalifying parts, and redesigning obsolete technology. NASA therefore turned to a new path with the Space Launch System, while SpaceX gambled on Starship, each costing billions and demanding years of unrelenting tests before proving reliable. Starship towers 120 meters high, surpassing even Saturn V in scale and ambition, designed to carry more than 100 metric tons to orbit. Its stainless steel body, methane-fueled Raptor engines, and massive payload capacity promise a revolution in heavy lift. Yet promises remain unfulfilled until sustained success replaces fiery failures that dominate test footage. Multiple prototypes have exploded during ascent, descent, or landing, spectacular failures that double as lessons in plumbing, guidance, and materials. Elon Musk insists the only path to rapid progress is to fly, fail, and fix, a mantra accepted by engineers but watched nervously by NASA. Aerospace analyst Laura Forzik notes that reliability, not size, is what truly matters for crewed missions, and Starship has yet to demonstrate that essential consistency. One of the most daunting challenges is orbital refueling, a maneuver never attempted at scale in spaceflight history. Artemis requires Starship to rendezvous with tankers in Earth orbit, transfer cryogenic methane and liquid oxygen, and store them without significant boil-off. Each transfer must work flawlessly, because even a minor valve malfunction could strand astronauts on their way to the Moon. NASA Flight Director Norm Knight has called this the most mission-critical leap in Artemis, a step more complex than Apollo docking maneuvers. SpaceX engineers are developing chilling techniques, double-wall insulation, and new pumps to prevent propellant loss. Yet skepticism lingers among experts like former astronaut Garrett Reisman, who warns that zero-gravity refueling is an engineering mountain not yet climbed by anyone, and rushing could backfire disastrously. Even if Starship reaches lunar orbit fully fueled, the Moon itself is a hostile landing site that resists human hardware. Surface temperatures swing nearly 250 degrees Celsius between day and night, punishing thermal control systems. Lunar regolith is composed of razor-sharp dust grains that infiltrate seals, corrode joints, and clog radiators, a problem Apollo astronauts reported after just a few days. Unlike Mars or Earth, the Moon's lack of atmosphere denies parachutes, forcing landers to rely solely on rocket thrust for descent. This requires precise engine throttling and massive reserves of fuel to decelerate safely. NASA engineer Clive Neal describes lunar dust as the most abrasive material humans have ever encountered, reminding designers that every landing pad must withstand decades of bombardment. SpaceX has floated ideas such as building hardened pads with robotic systems, but these remain conceptual. These barriers make Artemis less a straightforward mission and more a rolling laboratory for humanity's future beyond Earth. Each technical hurdle solved could seed innovations across multiple industries, from cryogenic storage to advanced robotics, propulsion, and radiation shielding. Success with Starship would not only mark a return to the Moon, but also open scalable transport for Mars, asteroids, and deep space exploration. Failures along the way, though costly, will teach lessons impossible to replicate in simulations or models. Aerospace historian John Logsdon emphasizes that Apollo showed what was possible, but Artemis is about permanence and infrastructure. Can Starship truly rise from prototype explosions to become the workhorse of lunar logistics? And could Artemis transform SpaceX into the launch pad for humanity's first giant leap toward Mars? The 20th century moved with an intensity that seems almost impossible today, a rhythm shaped by total war and existential rivalry. In the 1940s, American shipyards produced aircraft carriers at the astonishing pace of one per month, floating steel giants with breathtaking speed. At the same time, the Manhattan Project compressed fundamental science, engineering, and logistics into just 3 years, producing the world's first nuclear weapons. Political urgency cut away bureaucratic layers, and budgets flowed without restriction, because victory was more important than efficiency or safety. It was a culture that rewarded results above all else, and it left behind both triumph and trauma in equal measure. The world of the 21st century operates under very different rules, defined by caution, oversight, and an expectation of accountability at every step. Building a Ford-class aircraft carrier now requires more than a decade, even with modern tools and automation. America's nuclear modernization plan is scheduled across 3 decades, despite drawing on existing knowledge and experience. Infrastructure faces similar challenges, as New York's 2nd Avenue subway expansion needed 17 years just to complete 3 stations. Legal reviews, environmental studies, community debates, and political hearings are now part of every project, slowing progress but reflecting the reality of democratic societies. NASA historian Roger Launius has observed that society no longer tolerates speed at the expense of safety, and that cultural shift extends directly into space exploration. For a time, SpaceX seemed like an outlier, the one company capable of reviving the urgency of the past with a modern twist. The Falcon 9 rocket became a symbol of rapid iteration. As launches stacked up, boosters landed and costs fell dramatically. Improvements appeared flight by flight, with engineers adjusting hardware and software in weeks rather than years. This pace gave SpaceX dominance in the satellite launch market and a reputation for doing what others called impossible. Yet when Starship entered the stage, even SpaceX collided with the realities of scale, regulation, and global scrutiny. Starship's enormous size, its methane-fueled Raptor engines, and its role in Artemis triggered a new level of oversight from agencies like the FAA, the EPA, and NASA itself. Every test now requires environmental assessments, safety reviews, and formal approvals that stretch timelines from months into years. Explosive prototypes, once accepted as part of learning, now draw national headlines and political pressure. Former NASA Administrator Jim Bridenstine has pointed out that public-private projects cannot move at the speed of private capital alone. They carry the weight of taxpayer money and international partnerships. SpaceX, once the rebel, now plays by rules written for national programs, transforming its startup speed into something closer to government speed. This slowdown, however, carries both risk and reward. On one side, SpaceX loses the nimble advantage that once set it apart, facing delays that frustrate both engineers and enthusiasts. On the other side, each pause adds safety, transparency, and legitimacy, essential qualities when human lives and billions of dollars are on the line. The modern world may move more slowly, but it also seeks to move more carefully, building systems designed to last longer and withstand greater scrutiny. For Artemis, this patience could prove vital, turning setbacks into safeguards and delays into durability. So the question becomes unavoidable. Is slowness the enemy of progress or its quiet foundation? And if Artemis crawls rather than sprints, will the outcome still be worth the decades of waiting? Financial strain has reshaped Artemis into something Apollo never was. A network built across borders and sectors. Instead of one nation carrying the burden, NASA has pulled in the European Space Agency, Japan's JAXA, and the Canadian Space Agency, each adding hardware, modules, and expertise. Private players like SpaceX and Blue Origin now anchor missions once monopolized by governments, proving exploration can be sustained through cooperation rather than rivalry. Political scientist John Logsdon has called this shift a new model of shared ownership. a structure that may outlast individual programs and administrations. What was born from scarcity has become a foundation for unity. Technical difficulty, far from being a dead end, functions as fuel for invention. Starship itself is a laboratory in motion, a stainless steel giant that forces engineers to solve problems under fire. Explosions, cracks, and delays translate into better alloys, stronger engines, and smarter fuel systems. These breakthroughs ripple outward, from aerospace to energy storage and robotics, industries that benefit far beyond the launch pad. Analyst Casey Dreyer notes that innovation thrives not in ease, recovery. The obstacles that look like setbacks may in fact be Artemis's greatest contributions. Politics, too, have evolved from the bipolar rivalry of the Cold War into a crowded arena where no single actor dominates. NASA is no longer the lone banner carrier of humanity's space ambitions. Instead, SpaceX has emerged as a commercial symbol of daring, while international agencies represent diplomacy and stability. This diversity of players, according to historian Roger Launius, creates resilience. No one cancellation can end the journey when so many are invested. Competition has softened into collaboration, and the moon becomes less a battlefield than a meeting ground. Even safety concerns, which seem to slow progress, build a sturdier platform for the future. Each delay adds new systems of protection for astronauts who will one day attempt even longer voyages. Lessons learned in capsule design, heat shielding, and environmental control now accumulate not for one mission, but for a sustainable presence. Former astronaut Chris Hadfield has argued that safety is not the enemy of exploration, it is the condition that allows it to continue. The caution that frustrates observers today could save crews tomorrow on the multi-year journey to Mars. So the question lingers like an open horizon. Will these obstacles forge SpaceX into the icon of a new space age? And is the moon, with all its challenges, simply the first step toward a far greater frontier? Apollo proved that humanity could touch the moon, but Artemis and SpaceX are aiming for something far more ambitious: to stay, to build, and to expand. The obstacles of money, politics, safety, and technology are not failures, but stepping stones that shape a stronger foundation for the future. Every delay hides lessons, every explosion sparks improvements, and every compromise brings us closer to sustainability. If even SpaceX, with all its daring speed and boldness, finds the moon a challenge, it shows how immense the goal truly is. Yet that struggle is what makes the dream worthwhile. Because overcoming these barriers does not only bring us back to the moon, it prepares us for Mars and for the stars beyond. The real question is not whether we will return, but when and who will be the first to make humanity's giant leap permanent.